Now we're going to cover a new type of proof. This is called proof by contradiction. So we'll first talk about what a contradiction means in mathematics. So it has a somewhat broader, it has a broader meaning than it has in English. So in math, a contradiction is a statement that is clearly false. So some examples, the statement 1 equals 2, that's a clearly false statement, right? So there are some statements that, aren't clearly false. So those would probably not be called contradictions, but this is a statement that's clearly false. Here's another one, 2 is not equal to 2. That's a clearly false statement. There exists an integer that is both odd and even. That's a false statement. It's clearly false because every integer is obviously either odd or even. Here's another one. The number 23 is prime and the number 23 is not prime, right? So it's not possible for both halves of the sentence to be true. So the entire sentence is therefore false because we're using the word and. Even if we didn't know whether 23 is prime, right? Even if we didn't know whether 23 is prime, but I'm saying A and not A, or whatever, I'm saying S and not S, that sentence is obviously not true because something cannot be both prime and not prime at the same time. Okay, so now we're going to use this idea of contradiction to help us with a new type of proof. So here's an outline for proof by contradiction. We start out with a proposition. Now, in the earlier proofs that we learned about, always the proposition was of the form if P then Q. If P then Q, right? It was an if then. But for proof by contradiction, that's actually not necessary. You can start with a proposition R, just a claim. Doesn't have to be of the form if P then Q. It could, often it is, but it often is of the form if P then Q, but it doesn't have to be of that form. So we'll see examples, three examples of proof by contradiction. The first two will be of the form if P then Q, but the last one will not be of the form if P then Q. Will just be a claim, not in a conditional form, and we're still going to be able to use proof by contradiction for that. So that's what the proposition looks like, and then we start with the proof. And what we do in the proof is suppose not R. In other words, we suppose that the proposition is false. Meaning, at this point, we don't know if the proposition is true or not, right? We're trying to prove that it's true, but we don't yet know that it's true. So we start off by guessing that it's false. You guess that the proposition is false. We do some work, and here's where the magic comes in, or the pain, whatever. It's this is where the problem comes. We have to do a lot of work here, and our ultimate goal is to show a contradiction. Our goal is to show that by supposing not R, but in other words, by supposing that the proposition is false, we get a contradiction, and that's the proof. So what's the logic behind this? So here's the logic. Here's the idea. As a direct result of guessing that the proposition is false, we obtain a contradiction, which is definitely false, right? In other words, as a direct result of guessing that R is false, we obtain a contradiction, and we know a contradiction is false. But we can have a false statement. In other words, in math, there cannot be anything false. So the proposition must be true, because when we guess that the proposition is false, that led to something that was false. So the proposition itself must be true, because if we assume that it's false, if we assume the proposition is false, we get something that is definitely false. So here's our first example of proof by contradiction. So we have the following proposition. Suppose A is an integer. If A squared is even, then A is even. Right? So this is a claim being made about every integer, even though we don't say explicitly for all integers. But we talked about in the past that in math, when we have a sentence of the form if P then Q, we're using some variable that's not a specific value, then it applies to all integers, even though we don't explicitly say for all integers. So if I have a case where A squared is even, then A must be even. Now this probably can be proved using direct proof. You can try doing it. But here I'm going to show how to do it using a proof by contradiction. So for the sake of contradiction, suppose that the proposition is false. Now, In other words, again, the first part of a proof by contradiction is we suppose that the proposition is false, meaning we suppose that this sentence is false. Now, this phrase here, for the sake of contradiction, you don't have to write that, but the reason I'm writing it is it's good style to write it because you're alerting the reader, you're letting the reader know that you're explaining to the reader what you're doing and why, right? In other words, normally, what's the justification for supposing that the proposition is false? Like, why would you do that? Why would you suppose that? You're explaining, why am I doing this? Because I want to obtain a contradiction. I want to show that by supposing the proposition is false, we get a contradiction. Okay, now, what does it mean to say that this is false? That if a squared is even, then a is even. So in other words, we want to negate an if-then statement, right? We want to negate a conditional statement. So if you remember, how do we negate a conditional statement? So what we do is the negation of a conditional statement says that this part is true. Whoops, this part is true, but this part is false. That is, suppose that a squared is even and a is not even, right? The proposition says if a squared is even, then a must be even. But we're assuming the negation of that. We're assuming that a squared is even, and yet a is not even. Okay, so now if a is not even, then a is odd. So a is equal to 2b plus 1 for some integer b. Okay. So what does that mean? So now so what is a squared? So a squared is 2b plus 1 squared, which is 4b squared plus 4b plus 1. Which is equal to 2 times 2b squared plus 2b plus 1, which is even, right? Because it's 2 times an integer plus 1. Okay, so far, okay, so in other words, a squared is even. Sorry, which is odd. I'm sorry, this is odd. Sorry, wrong word. It's odd. So this is odd, so a squared is odd. But hold on, we are supposing that a squared is even. Right, we're supposing that the proposition is false, which means that a squared is even. So here we have a contradiction. So therefore, a squared is even and a squared is odd, which is a contradiction. So the proposition must be true. Why? Let's explain. We started by guessing that the proposition is false, right? That guess directly led to a contradiction. And the only cause for that contradiction was that guess. The only reason we got this contradiction was because we guessed that the proposition is false. Now, since a contradiction cannot exist in math, we assume at least, so therefore our guess must not be correct, right? Because our guess led to a contradiction. Our guess was that the proposition is false. So in other words, the proposition must be true. Next example of proof by contradiction. Here's the proposition. If a and b are integers, then a squared minus 4b is not equal to 2. So what this means is no matter what a and b are, right? A and b could be any integers. You'll never come up with a case where a squared minus 4b is equal to 2. In other words, it's always not going to be equal to 2. A squared minus 4b is always not going to be equal to 2 when a and b are integers. Okay, so let's start the proof by contradiction. So assume for the sake of contradiction that there exist integers a and b for which a squared minus 4b equals 2. In other words, we're assuming that the proposition is false. We're guessing in a way that the proposition is false. In other words, we are guessing that in fact there are integers a and b for which a squared minus 4b is equal to 2. The proposition says that should not exist, but we are assuming that the proposition is false. Okay. Now, if we have integers a and b for which a squared minus 4b equals 2, then a squared minus 4b equals 2, which means, well, I can add 4b to both sides, right? I can add 4b to both sides, so I have a squared equals 4b plus 2, which shows me that a squared is even because a squared is equal to 2 times b plus 1, so a squared has to be even. Now we know that a squared is even. Seems to be missing a word here. I should say here, which is even or something, but okay. All right, so we see a squared is even. Now, based on the previous proof, what do we know? Well, from the previous proof, we have seen that if a squared is even, then a is even, right? That's what we just proved. So based on that, we're going to use that result here. Right? We're going to say, since a squared is even, which we show here, right? A squared is equal to 2 times b plus 1. Since a squared is even, a must be even. Okay, so now if a is even, what does that mean? That means a is equal to 2 times c for some integer c. Okay, great. Let's go a step further. What happens if a is equal to 2 times c? Well, then remember we have that we started with the assumption that a squared minus 4b is equal to 2. Well, we know a is actually 2 times an integer c, so let's write it like that. 2c squared minus 4b equals 2, which means 4c squared minus 4b equals 2. We can divide both sides by 2, which gives us 2c squared minus 2b equals 1, which means what? Well, we can factor it like this: 2 times c squared minus b is equal to 1. Now, what does that mean? That means, well, this is the form of an even number. So that means 1 is an even number. Therefore, 1 is even, which is definitely false. All right, 1 is not even. I mean, you can show that formally, but it's almost obvious, right? You can show that there's no way to make it so that 2 times an integer is equal to 1. Anyways, 1 is even. It's definitely even. We all accept that. So this thing here, I'm sorry, 1 is odd. I'm sorry. We all know 1 is odd. I'm sorry. So this thing that says that 1 is even is definitely false. Thus, our assumption must be false, because our assumption that there exists a and b for which a squared minus 4b equals 2 directly led to this line here, which says that 1 is even. So our assumption must be false, and therefore the proposition must be true. And the assumption was just that the proposition is false. So that assumption leads to this contradiction. So therefore the proposition must be true. Okay, now before we do our third example of proof by contradiction, we're going to talk about rational numbers. So you've seen this before, I assume, but a number x is rational if x can be written as a divided by b, right? X equals a divided by b, where a and b are integers, and b is not equal to 0, right? If b would be 0, then this would not be a rational number, right? So like 5 divided by 0 is not a rational number, but b could be any other integer, and a could be any integer. So if a number can be written as a divided by b, where a and b are integers, and b is not equal to 0, then that number is rational. On the other hand, if x is not equal to a divided by b for every possible integer a and b, then x is irrational. Meaning, in other words, if there's no way to write out x equals a divided by b, then x is irrational. Okay. Now, some examples: 6 divided by 23 is a rational number. Right? 6 is an integer, 23 is an integer, 23 is not 0. This is a rational number. The number 23 is also a rational number, right? Just 23 by itself is a rational number. Now that's not maybe so obvious, but here's why. Since 23 is equal to 23 divided by 1. Right? So since 23 can be written as a divided by b, where a is an integer, 23, and b is an integer, 1 in this case, and b is not 0. So therefore 23 is rational. Now, here's a little note, which is really nothing to do with rational numbers. It's more a general thing about fractions, okay? And we're going to use this note, we're going to use this idea in the next proof. So first of all, a fraction a divided by b is said to be in simplest form. We say it's in simplest form if a and b have no common factors other than 1. Meaning there's no way to simplify it further, right? It's in simplest form. Now, every fraction a divided by b, where a and b are integers, is either already in simplest form or can be converted to simplest form. All right, so given any fraction where of two integers, right? Given one integer divided by another integer, it's either right away in simplest form or it can be converted to simplest form. So in other words, if I give you a fraction, I can say let that fraction be in simplest form, which means either it's already there or just convert it to simplest form. Okay, now we're going to do our next example of proof by contradiction. And the proposition that we want to prove is that the square root of 2 is irrational, right? So notice in the previous examples, I only gave examples of rational numbers. If you want to show that a number is not rational, what you have to kind of show is that it's impossible to write that number as a divided by b, which is not an easy thing to do. So we're going to try to prove that this specific value, square root of 2, is irrational, meaning there's no way to write square root of 2 as a divided by b. And we're going to use proof by contradiction. Now notice here, the proposition is not in the form of if p then q. It's just a proposition, just making a statement, a claim, not in a conditional form. But we can still use proof by contradiction here. We would not be able to use direct proof, really, or at least it wouldn't be obvious how to use direct proof or contrapositive proof. But proof by contradiction will work. But I should say, I should have said this maybe before. Proof by contradiction can be, often is more difficult than direct proof or proof of the contrapositive proof. It's more, proof by contradiction is usually more difficult, or often is more difficult, and that's because, right, the problem is we know we want a contradiction, but it's not clear about where the contradiction is going to come from. So in a direct proof, you know what you want to get to. In a proof like in a contrapositive proof, you know the ultimate goal. You know exactly where you want to get. Just the question is how to get there. But in a proof by contradiction, you know the general thing that you want a contradiction, but you don't know exactly the contradiction that you're looking for. It's not like I want to find this specific contradiction, and I just need to get there. It's rather that you want to find just a contradiction. And that contradiction could be anything, could be any contradiction. And so you just have to try out different things until you find a contradiction. Okay, so here's the proposition we want to prove. And so let's start doing the proof. So suppose, for the sake of contradiction, that the square root of 2 is rational. In other words, we're supposing that the proposition is false. So we're supposing that square root of 2 is rational. Okay, then square root of 2 is equal to a divided by b for some integers a and b. Okay. Let this fraction be in simplest form, meaning either it's already in simplest form, and if not, convert it to simplest form, which can always be done, right? You can, if a fraction is not in simplest form, you can always convert it to simplest form. Okay, so there's an algorithm, pretty simple algorithm for converting a fraction to simplest form. Maybe if you want a very efficient algorithm, it's more complicated. But if you don't care about efficiency, you can make a very straightforward algorithm. Just keep dividing by 2 as long as it's possible to keep dividing by 2, and right, as long as a and b are even, just keep dividing them by 2 until one of them is odd. Right. So, anyways, whatever. You don't have to understand that algorithm, but the idea is every fraction can be put into simplest form. So let this fraction, right, this a divided by b, let this be in simplest form, whatever it is. We don't know what a and b are, but let that fraction be in the simplest form. Now, if the fraction is in the simplest form, that means that they have no common factors, right? They have no common factors. So if they have no common factors, that means that it's not possible for both a and b to be even, because if both a and b are even, that means they have a common factor of 2. So it's not in simplest form. But we want the fraction to be in simplest form, which is possible to do. We can always make the fraction in simplest form. So if it's in simplest form already, then which we've done, we've said it's in simplest form, or we've put it into simplest form, then a and b cannot both be even. At least one of them has to be odd. Okay. Now, since square root of 2 is equal to a divided by b, what we have is the following. We have, well, we can square both sides. Right, so we can do square root of 2 squared, and that's equal to a divided by b squared. This on the left simplifies to 2, And on the right, you might remember this, right? When you have a fraction raised to the power of 2, or raised to the power of anything, raised to an exponent, the exponent can be placed on the numerator and on the denominator like that. So 2 is equal to a squared divided by b squared. Now, I would suppose I want to clear this b squared from the bottom here, right? I want to turn this, I want to make this not anymore a fraction. So in other words, I can multiply both sides by b squared, which gives me 2b squared is equal to a squared. So what does that show me? What does this show me? Well, it shows me that a squared is even, right? Because a squared is equal to 2 times an integer. B is an integer, so b squared is an integer. So we have 2 times b squared. So in other words, a squared is even. Again, all we're saying so far is that a squared is even. Okay. But now from the earlier proof, from the first example of proof by contradiction that we did in this video, we showed that if a squared is even, then a has to be even. So continuing the proof, by an earlier proof, since a squared is even, a must be even. Okay, so a is even, fine, so a is even. Well, we said just before that it's not possible that both a and b are even. At least one of them has to be odd. So if a is even, well, first of all, a is equal to 2 times c for some integer c. But also, since a and b cannot both be even, b must be odd. Right? B must be odd because a and b cannot both be even. And we know a is even, so b must be odd. Okay, no problem. Since a is even, we have that, well, now, so we're reusing what we had before, right? We had that 2b squared is equal to a squared. So now we're reusing that. So 2b squared is equal to a squared, but now we know that a is equal to 2 times c. So we'll write that as 2b squared equals 2c squared. Now, now what does this mean? So 2b squared equals 2c squared. Well, so 2b squared is equal to 4c squared. We can divide both sides by 2. So b squared is equal to 2 times c squared. So what does that tell us? Well, this tells us that b squared is even, right? Because b squared is equal to 2 times an integer. So, right, c is an integer, c squared is an integer. So b squared is equal to 2 times an integer. So b squared is even, but by that earlier proof, b itself must be even, because if b squared is even, then b is even. Okay, so now what do we see? Therefore, b is even and b is odd, right? We concluded here that b must be odd, and here we concluded that b must be even. So therefore, b is even and b is odd, which is a contradiction. Cannot be true. Now, what led to this contradiction? The only unjustified assumption we made was that the square root of 2 is irrational. Right? That's the only unjustified assumption we made. Everything else was perfectly logical, perfectly reasonable. So clear logic should not lead to a contradiction. Should not lead to something that's false. If it does, that means we made a mistake along the way. The only thing that could be mistaken, the only thing that was not justified in what we did was our assumption, our initial assumption that square root of 2 is irrational. Since that assumption led to something that is definitely false, that assumption must be false. Thus, we can conclude that the square root of 2 is irrational, which is what we wanted to prove in the proposition. That's the end of proof by contradiction.